Unit 2, which had the theme of smells, covered chapters 6 through 8. This unit established an understanding of molecules through tangible experience. You began examining smells and molecular data for several compounds. Then you formulated a hypothesis based on patterns in the data that relate smell and molecular structure. You continued to test and refine your hypotheses throughout the unit while exploring molecular formulas, Lewis dot symbols, structural formulas, polarity, molecular size, and shape, and bonding patterns. You also learned how to identify specific functional groups within a molecule. Lastly, you looked at a theory for how molecular shape and structure is related to the smell of a molecule and how the olfactory system works to interpret the smell a molecule has. So for chapter 6, which was titled Speaking of Molecules, it was our first introduction to covalent bonding and structural formulas and Lewis dot structures, isomers, all of that. So we first, if you remember, smelled a couple of different oils, a couple of different compounds, and we classified the smell as sweet, putrid, fishy, or minty at first. And we tried to relate the molecular formula that we were given to the smell. And we found out first that the things that had 2 oxygen atoms smelled sweet, 1 nitrogen atom smelled fishy, the 1 oxygen atom smelled minty. Those were the first things that we looked at. And then more smells were introduced as we built upon the chapter. We looked at the idea of a molecular formula as just saying the number and type of elements that are in a molecule that's covalently bonded, only nonmetals. The structural formula provides more information about how the atoms are connected together. Isomers we were introduced to, and isomers any 2 or more chemical compounds that have the same molecular formula, so the same number and type of atoms or elements in the compound, but they're connected in a different way. So in other words, their structure is different. They have different structural formulas. A couple examples I gave you here: butane, isobutane, 1-propanol, which has the OH here on the first carbon, and 2-propanol that has the OH on the second carbon. If you count in these two and in these two, they have the same number of carbons, hydrogens, and oxygens, but they're connected in a different way. That makes them isomers. And because they have different structures, they're going to have different properties. Structural formula shows the connectivity of atoms in a molecule. It's how they're bonded together. We don't include dots technically in a structural formula. We reserve that for Lewis dot structures. We then looked at several different structural formulas and the patterns that we found in how hydrogen, oxygen, nitrogen, and carbon bond. And we came up with that hydrogen bonds once, oxygen bonds twice, nitrogen bonds 3 times, and carbon bonds 4 times. And we came up with HONC 1, 2, 3, 4 as the rule to help us draw structural formulas. The reason why these things form the number of bonds they do has to do with the number of valence electrons they have and how many valence electrons they need to have 8 total, right? So the fact that the oxygen needs 2 more valence electrons, it's going to bond twice to get them. Lewis dot symbols for elements just show the number of valence electrons in the outer shell for that particular element. Which of the following structural formulas is incorrect based on HONC? The one other thing we want to include here with HONC, this is oxygen, nitrogen, carbon, and any other elements in their respective groups, because in the similar group they have the similar valence electrons, same number of valence electrons, so they're going to bond similarly. Hydrogen, the H can stand for hydrogen, or the halogens, which is 17. So group 17, like chlorine here, will bond once as well. So this one's good. Carbon has 1, 2, 3, 4. Carbon has 1, 2, 3, 4. Each hydrogen has 1. That's good. Carbon has 1, 2, 3, 4. The oxygen has 1, 2. The hydrogen has 1. The oxygen has 1 to the carbon and then 1 to the oxygen. That's not written, but it counts. This carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4, 5. So that's our problem there. That structural formula is incorrect because carbon is showing 5 bonds there when it should only have 4. Draw 5 possible isomers that exist for the molecular formula C5H12O2 following HONC 1, 2, 3, 4. I'm going to draw one for you, and then you can draw several others. We want to connect all of the carbons first. Then we place the oxygens or nitrogens. I'm going to place 1 oxygen here. And then we go around and fill in with hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I make sure that honk is being followed. All my carbons have 4 bonds. All my hydrogens have 1 bond. My oxygen has 2. If honk is not being followed after you add all the atoms, then that's when you have to include double or triple bonds to make sure that honk is being followed. We'll do 1 just to show how it's an isomer. I can do 1, 2, 3, 4. Let's do 5 here. I'm going to put my oxygen there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12. So that's another isomer, similar molecular formula, or same molecular formula, different structure. Molecules that we draw using structural formulas and Lewis structures are held together. The atoms are held together by covalent bonds, which is a bond that connects 2 atoms together from the sharing of valence electrons. So each atom in the bond brings an electron to the table to share. The atoms overlap, and that pair of electrons, bonding pair, is what forms the bond. All the other electrons that are not participating in the bond are called lone pairs. So here between HCl you have 1 bonded pair that represents 1 bond, just a single line, and then the 3 lone pairs on chlorine. Lewis dot structure shows the unbonded valence electrons in a molecule as dots. So it's basically a structural formula with dots. We can draw Lewis dot structures in one of 2 ways. Either show everything as dots, the lone pairs end the bonds, or we can show the bonds as lines and the lone pairs as dots. So both of these 2 things mean, got to add 2 lone pairs there. These mean the same thing, and these 2 things mean the same thing. Remember, hydrogen never gets lone pairs. It's always going to be on the outside of a molecule because it's going to only make 1 bond. The trick for the lone pairs is you're going to, after drawing the structural formula, add enough lone pairs so that each atom has 8 valence electrons around it, right? The octet rule. The trend for bonds and lone pairs, things like carbon in group 14 will have all 4 bonds. Group 15 will have 1 lone pair and 3 bonds. Group 16, 2 bonds and 2 lone pairs. And then group 17, hydrogen or the halogens, will have 1 bond. And then the halogens will have, add another lone pair here because it was missing, we'll have 3 lone pairs. We look at different types of covalent bonds, meaning single, double, and triple. Single bond is just 2 electrons being shared, 1 pair. A double bond is 4 electrons being shared, 2 pairs, which we represent with 2 lines there, like an oxygen. Or in nitrogen, there's a triple bond, which is 6 total electrons being shared, 3 pairs of electrons being shared there. The oxygen molecule here, if we can just fix this for a minute, should have 2 lone pairs like that. I don't know why the dots showed up like that. Cross out these dots up top, and the nitrogen should have just 2 electrons on the side like that. So cross out the dots for top and bottom there. Gave you another image just to show how you can represent single, double, and triple bonds if you're just including dots. If you don't want to include the dots, then for each pair, you draw a line to represent the bond. The last bit in chapter 6 was then relating the idea that we couldn't only relate on the molecular formula or structural formula to help us with the smell that a molecule has, but we had to look at the functional group in the molecule. And the functional group were specific groups of atoms that are in a molecule that are responsible for the specific properties and chemical reactions of that molecule. And the ones we went over were alcohols, ketones, carboxylic acids, and amines, and esters. The conclusions we came up with, first of all, you should be able to relate the functional group to the name ending. So propionic acid has a carboxylic acid group in it. You should be able to pick out the functional group, that COOH at the end of the molecule is an acid. Its names end in acid. Esters end with the ate ending. It's the YL and then 8, so ethyl formate as an example. The ester is what looks like the carboxylic acid, but it's in between, it's in the middle of the molecule. The oxygen's in between two carbons, not on the end. Ketones, we said smell, in this chapter we said smelt, the only ones we smelt were minty. We developed that further as the chapter went on. We saw that they could be other smell, they could fit into other smell categories. But to recognize a ketone, it's a carbon double bonded to an oxygen in the middle of a molecule. Its name ends in -one. Alcohols have an OH, just an OH group, not COOH like the acids, but just an OH group, and their names end in -al. And then amine has a nitrogen, their names end in amine. And what we concluded up to this point was that the carboxylic acids were the molecules that smelled putrid, the esters that end in -ate smell sweet, amines that contain the nitrogen smell fishy, the alkanes we saw a couple of, they smell like gasoline, so those are things like butane, propane, octane like gasoline. Alcohols and ketones were the things we later developed further. We know that those two things could fit into 3 possible smell categories depending on the shape of the molecule, but we didn't look at shape yet. So for alcohols in this chapter, the most we saw was that they smelled medicinal, right, was the term that we used. And then for ketones, that they smelt minty. The last thing we did in this chapter, in terms of the last lesson and last lab, was look at a synthesis reaction between 2 compounds that had really undesirable smells. We mixed in alcohol, which was medicinal smelling, with a carboxylic acid, which was putrid smelling. And we caused a synthesis reaction to occur, which means the creation of specific compounds through controlled chemical reactions. What we did was we made an ester. If you remember, we mixed those 2 really smelly compounds in the test tube, we heated them up, and then afterwards we got a sweet smelling molecule. That was our first introduction to what a chemical reaction was, which is a process that results in chemical change of a substance producing new compounds with new properties. That's really important because this was sort of the foundation for a lot of other things we looked at throughout the year. It results in a chemical change, which means we're changing what the substance is, producing new substances, and if they're new substances, they contain new properties. You're not going to be responsible for looking at the mechanism, right, breaking the bonds and forming the bonds. We did that in class, and we did examples, but for the final exam, you're not going to be responsible for taking an alcohol and an acid and determining what the ester is, but you should know that we used those examples to show what a chemical reaction is and how we can take 2 things that have really, really different properties like their smell, which were undesirable, and after they went through a chemical reaction, their properties changed because the actual chemical composition of the substance changed. And that's where we ended off with chapter 6.